After a very nice introductory lecture of Luca, I will just use some of results which he so rigorously derived. And I will talk about gravitational effective field theory of general relativity. And today I will not be talking about positivity bounds technique. I will be talking about that tomorrow. But today I will give an introduction of what is effective field theory of gravity, what kind of interactions we have, and what is the structure of this theory, how it can be written, how it can be reduced. So let us start with the graviton propagator and Feynman rules for general relativity. In harmonic de Donder gauge, which Luca introduced, so I'll be working in this gauge. Nabla h mu minus 1/2 eta mu nabla h alpha alpha equal to 0. Here, eta mu is a flat space metric tensor. I'll use, as usual, minus plus 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 signature. And then the propagator of graviton in GR in space coordinates can be written as a Fourier transform of momentum space propagator. And it can be written as x minus y d4q over 2 pi to 4 I over q squared plus I epsilon. It's some standard parameterization of propagator of the particle in quantum field theory. And I will add the tensor structure, which is coming in the form of tensor, which I will call as P alpha beta gamma delta. And this tensor, P alpha beta gamma delta, is equal to a combination, particular combination of metric tensors, flat space metric tensors. Eta alpha gamma, eta beta delta, plus eta alpha delta, eta beta gamma, and minus the combination which is alpha beta gamma delta. It corresponds to the propagation of the graviton with indices h alpha beta is propagating to indices h gamma delta. So the minus sign corresponds to the combination of indices, same as indices of propagating graviton. So that's the first Feynman rule for the graviton. Then if we want to consider scattering and scattering amplitudes mediated by gravity, we need a vertex between matter and gravitons. To derive things on the blackboard, I prefer to use the simplest case of minimally coupled scalar interacting with gravity. So the corresponding Lagrangian I consider at this moment would be for the action. Let's work in 4 dimensions. And it's the GR action. Here I put Planck mass instead of kappa constant, but Planck mass squared. Minus 1/2 d mu phi squared. And I want to find a vertex between graviton and the scalar field. So I need this 3-point interaction. Phi phi h mu. How can I find it from the Lagrangian? I need to take, since this vertex will come from the term, from the kinetic term of the scalar field, I need just to take a variation with respect to metric of this scalar field. Apparently, it can be written in the form delta S is equal to integral d4 x root minus j. And one of the variation of the metric comes from root minus j, and it will come with 1/2 h mu nu. D mu phi squared uh, 1/2 h mu nu plus h mu nu coming from d mu phi squared written in a proper way like g mu nu d mu phi d nu phi. Here g mu nu is explicit, so I'll have a combination h mu nu multiplied by d mu phi d nu phi. And here I need the eta mu nu, flat space metric. So I have two combinations of vertices contributing to this Lagrangian, and 1/2 is this 1/2. This 1/2 is coming from differentiation of square root of j. So I have a combination corresponding to 3-point vertex between scalar and graviton. Apparently, this vertex v mu nu will be equal to I 1 over root 1 2 Planck mass. And then if this phi field has a momentum p1 and this one has momentum p2, we can from that we can derive that it's p1 mu p2 nu plus symmetrized combination p2 nu p1 mu minus eta mu nu p1 gamma p2 gamma. So all of this action can be obtained directly from the interaction Lagrangian. Then, if we want to consider the simplest scattering amplitude, which is three-level scattering of scalar particles through the graviton, we can draw a diagram like this. And let's define it like P1 goes here, P2 goes here. Name it P3, P4 goes. So for all ingoing momenta, this combination, I'll call it all ingoing momenta, which means that all momenta are directly going to the diagram. Yes. Yes, P1, P2. I can write it also like contraction of P1 and P2. I consider massless scalar here for simplicity.
Second term is P2.
Yeah, P1, P2. P1, P2. So it should be a symmetrized combination of P1, P2.
One, no, two mu, right? But they're the same.
Sorry, indeed. Yeah, the idea is that it's a symmetrized combination of this momenta. So having this vertex, our purpose is to compute how scattering amplitude of gravitons look like. What is the dependence of scattering on the momenta and finally on the Mandelstam variables. We'll come to that soon. So for this particular diagram, we have momentum, we have the amplitude, which I'll call ms, which means that it's kind of S-channel amplitude, as it will contain P1 plus P2 in the propagator. So here we have P1 plus P2 combination. In order to compute this, I need to take imaginary unity and contract V mu nu taken off P1 and P2. I need to contract it with the propagator, which has a simple part P1 plus P2 squared, and this tensor P mu nu alpha beta V alpha beta of P3 and P4. So then we need just to contract everything, and to simplify the computation, I would note that V mu nu contracted with the propagator, V mu nu of P1, P2 contracted with the propagator P mu nu alpha beta will be equal to I over 2mp. And I will get just a combination of P1 alpha, P2 beta, plus P1 beta, P2 alpha. And the combination corresponding to P1, P2 will be actually cancelled. There are two terms which exactly cancel each other in, it happens only in 4 dimensions, actually. This is very simple computation. I don't think I should do it on the blackboard right now. So I mean, I need just to contract V mu nu here with the propagator written here, and very carefully convert all the tensor indices. The result would be quite short. It will be looking like this. After that, I can contract it with V alpha beta of P3 and P4, and this contraction would lead me like V mu nu P mu nu alpha beta V alpha beta. I will get I over 2mp V1 alpha V2 beta, and in principle, since V alpha beta is symmetric in alpha and beta, I can skip writing the second term. Instead, I can just add 2 or clean these 2 standing here. And for V alpha beta, I need to write carefully the same expression, but taken of the momenta P3 and P4. So it should be I over 2mp. And here a combination of momenta P3 mu P4 nu plus P3 nu P4 mu, and minus eta nu nu P3 P4. I get this vertex is suppressed by power 2 of Planck mass. Then yeah, I also need to change alpha and beta here, of course, sorry. And just carefully make a contraction. So contracting this, I get combination P1, P3, P2, P4. I got it from the first term. From the second term, I get P1 gets contracted with P3. Sorry, P1 gets contracted with P4, and P3 gets contracted with P2. And the last term, I get minus P1, P2, P3, P4. Okay, so this is the moment to introduce Mandelstam variables, and for the scattering amplitude with all ongoing momenta, whatever scattering we consider, the amplitude is a function of three so-called Mandelstam variables. And if I call the momenta P1, P2, P3, P4, I can introduce the variable S equal to minus P1 plus P2 squared, or by the energy conservation, it is the same as P3 plus P4 squared. So it is a scalar invariant, which is just square of certain momenta. For the T Mandelstam variable, I write P1 plus P3 combination, and the corresponding amplitude can be obtained from by crossing of the particles. So we just do exchange the particles, rename the particles, in fact. Or it is P2 plus P4 squared, which again doesn't matter. U is when you exchange particle momentum 2 and momentum 4, and it will correspond to P2 plus P1 plus P4 squared, or P2 plus P3 squared. Okay, in the massless case, we can very simply, since all the squares of the momenta are zero, we can write it like that S variable will be minus 2 P1 P2, T variable will be minus 2 P1 P3, or again minus 2 P2 P4. This is minus 2 P3 P4, and minus 2 P1 P4. So then I can simply substitute this knowledge to final amplitude and get minus 1 over 2 MP squared. P1 P3 is T minus T over 2 multiplied by minus T over 2 plus minus U over 2 squared, and minus minus S over 2 squared. Okay, then I will get minus 1 over 8 MP squared. And here I get T squared plus U squared minus S squared. And then remember that we have also we have also this denominator. And finally, for collecting all the factors, we get, for the S channel amplitude, we get 1/2 mp squared S t squared minus u squared minus s squared. And also it can be written as minus 1/mp squared tu over s. And this structure is very important because we see that there is a pole in the amplitude when s is going to 0, which will never be cancelled by any other parts of this amplitude. And also, let me mention that when we scatter massless particles, s plus t plus u is equal to 0. It's very easy to derive from energy conservation. So u can be written as minus s minus t. Sorry, here I have plus. And for the total amplitude, I need to sum up 3 diagrams. I need to sum up the diagram I already have, this one, plus this one, and plus this one. So this is what I call S, this I will call T, and this I will call U. And total amplitude will be minus 1/mp squared Tu over S plus St plus Su over T plus St over U. I can obtain it without computations, just exchanging the Mandelstam corresponding Mandelstam variables. So to get T channel, I need simply to change S to keeping U the same. I need to change S to T everywhere and T to S. Just exchange S and T, and here I exchange S and U. This way, without any computation, I can obtain 2 other channels of this amplitude. Question?
Yes. The factor of the difference comes from the fact that you can change external part, or because you have 1/8 mp squared, and then the so symmetry factor.
No, it's some factor which I have missed somewhere, because when I was multiplying, I had extra factor of 4 because I need to actually the quantity here is just this quantity, and I think I missed somewhere the factor coming like 2 coming from here. So I have extra factor. This factor 2 is taken into account. It's happening here. Okay, I think I need to verify this factor a bit later, but the textbook result is that we need to we obtain this kind of structure of the amplitude. What's important here that is that in the forward limit of scattering, forward limit corresponds to 0 momentum transfer. So particles with the same momenta are coming, like P1, P2 is coming to the same momenta P1, P2. So for us, it will be due to the for unitarity issues because of optical theorem formulation, forward limit will have a special meaning in this case. For the scattering through graviton, it corresponds to t going to 0. It happens when momenta of the particles don't change. So the questions? Okay. If momenta of the ingoing and outgoing particles are the same, then this limit corresponds to Mandelstam variable t going to 0. And if we expand this amplitude in the limit t going to 0, we obtain minus 1 over mp squared s squared over t.
Yes. There is a question online. What
Okay.
factor in the action decides the scale of the reaction process? At what energy should I expect this scattering?
There is only one dimensional parameter in this model, it's Planck mass. And basically, I will come to this a bit later, but this is the scale until which the theories can be trusted at all. So momenta about which we are talking about, all of them should be much smaller than Planck mass squared. Does it answer a question or? So then we can consider different limits of the scattering when momenta are of the same order, like S is of order t, but it is for many theoretical considerations, it's also very important to take a forward limit scattering of the scattering when one of these momenta is very small, and S in principle could be large. But if it goes larger than Planck mass squared, we cannot trust the theory anymore. But I'll explain it a bit later how it happens. But apparently here, let us notice that the forward limit structure of the amplitude is S squared over t, and there is a pole, there is a singularity when t goes to 0, which strongly affects many considerations of analyticity of the scattering amplitudes, and it will affect many conclusions about how gravitons can scatter, also including the UV limit. So what kind of computation? We can do another simple computation, which will basically show that we are dealing with not a complete theory. It's not enough to have just GR. I guess Luca will explain much more about this tomorrow during his lectures, but I will show some very simple computation, given that we derived Feynman rules, which shows that we need to add something more to the theory. It's not, we need to add some much more terms to this action. Among the simple computations, we can find the expression for this diagram, for example. This would be one loop diagram, and here the momentum L is running in the loop, and let's name it Q. It will be some contribution to the propagator of graviton, where matter loop is run, where some matter particle, here we consider scalar field, is running inside this loop. So it's phi field here. Since the expression for the vertex is relatively simple, I would say that if we consider 3 graviton scattering the corresponding expression will have about 100 terms if you expand it in momenta. And this is certainly not for a blackboard. But this is something easy to show. So this matrix element will be proportional to integral over momentum L over 2 pi squared I'm writing one of these vertices. I need to divide it by L squared, and there will be another vertex, L delta, L plus Q gamma, L gamma, L plus Q delta. And I divide it by L plus Q squared. So here there are some coefficients. But for me, I would be interested in the structure of the result of this loop diagram, and we can see that this integral is of the form d4L. Here we have loop momentum to the power 2 plus 2, 4, L to 4 in the denominator, and it's divided by L to 4 in numerator. So it will be some divergence which is proportional to lambda to 4. But since we have only one vector which is in this diagram, we know that we cannot get anything else but some combination of Q with 4 indices. So I just write Q alpha, Q beta, Q gamma, Q delta. And I know that my result is some divergence, one loop divergence, 1 over epsilon plus log Q multiplied by this combination, Q alpha, Q beta, Q gamma, Q delta. And it is proportional to momentum to 4. The problem is that if we expand, the problem is that we don't have a counter term to cancel this divergence, because R, if we remember what is curvature, it has only 2 derivatives of metrics. So it contains only 2 derivatives acting on some combinations of metric, maybe 4 metrics or 3 metrics. Whatever expansion we do, we cannot get anything proportional to D to 4, no term proportional to D to 4, which is required to cancel the divergence proportional to Q to 4. And from this, we have to conclude that the presence of matter requires some interactions which has 4 derivatives, and which definitely is not in the Lagrangian, not in the original Lagrangian. So the theory is not complete. And moreover, if we write some vertex reproducing this divergence, we will get more and more vertices proportional to 6 derivatives, 8 derivatives, and so on to infinity. So at least it's quite easy to show that gravity with matter will be not a renormalizable theory. So the correct framework for considering such theories is the framework of effective field theories, where we built a low energy description, which is valid only up to some scale. But since we have a lot of nice symmetries, we can track the structure of the series very well. And due to many features of the effective field theory approach, we have only limited number of terms which are relevant for any on-shell computations. So, as we concluded, it was not enough to have just general, equation.
I'm going with that if you do the same computation in 2D, like
Yeah.
you get probably something extra over. Get some q's, q squared with indices like q mu, q mu,
Yeah.
but also a q squared. And in gravity, why don't we get a q to the 4?
We get q to 4 because of the fact that there are derivatives in the interaction. In QED, we don't have derivatives in the interaction. In QED, if I remember correctly, the vertex was electric charge. If it's some electron, it's gamma matrix, d mu, a mu, right? Psi bar psi, yes. Psi here and I guess psi bar here. Okay. No, we should have a derivative, I guess. Okay, it's coming, not, yes, indeed, sorry. So we have just this combination and there are no derivatives in this term. The difference with gravity is that we must have h mu nu, d mu phi, d nu phi. In any case, we have derivative interactions which add more powers of momenta to Feynman integrals. And it's a generic problem. If you add more derivatives to the theory, you cannot make it renormalizable anymore. So here we just hit this problem.
So the question was literally get ever q to the power 4 with all indices subtracted and no indices left, or no? Q alpha, Q beta, Q
yeah, because if we consider this propagation h alpha beta, h gamma delta, we get some.
You need the
Yes, you need 4 indices. And the point is that I want to simplify my life a bit and say that since my integral depends only on one vector from Lorentz invariance, I know only one structure with 4 indices made of this vector. All the rest will reduce to this structure. Well, anyway, even if you have, you might also have some metric combinations like eta alpha beta, eta gamma delta, but the problem is that it doesn't solve your problem. It solves nothing. It's again something which has to be given by 4 derivative interaction. Okay. So more questions, yeah.
Due to this divergence, that appears when we couple a scalar field, we say the theory is not complete, but what about if we couple it to fermions, for example? Same structure.
It doesn't help because in any case you have the coupling is that the leading coupling to graviton comes from kinetic term of the fermion, which is psi bar, gamma mu, d mu, psi. So we still have a derivative here. It will not help much. It will have, of course, the structure will be a bit different, and it all can be computed, and the results, I think, are well known. But fermions cannot help to renormalize gravity. The value will be different. For fermions and scalars, for sure, they will be different. Some contributions, I think they should be of the opposite sign, and it was used in many some supergravity proposals people claim that many cancellations happen due to opposite signs between the fermions and scalars, but at the end they still get some divergence. Maybe at 8 loops, but it doesn't matter at what loop you get it. It just complicates the overall computation. Well, at least at this moment, it's not known that some very good symmetry can help in normalizing gravity. Okay, so I think I can give a couple of minutes for a short break if someone needs.
Hi.
Yes.
Sorry. Maybe my question wasn't clear, but I think I remember in QED you get something like this. And I was wondering if you had a term similar like this in gravity, or if you would always get just a term like this.
You get only four derivative terms, but in QED you can I think you will get some.
But can you, for example, get something like a Q squared metric term, where the metric hold the indices? Q to the 4, I'm sorry.
Yes, but
yes?
I think you can. Okay. Yes, but I don't think it helps.
Okay. No, of course, because it's still for derivatives, right? Yeah. Still non-renormalizable.
Yeah.
Okay.
So I just show it's like a power counting because, of course, the overall computation is very long.
Yeah. Okay. Thank you.
Mhm. Yes.
Continue. So we were looking when we were looking at the actual which we saw.
Okay, shall I proceed now? So before coming to consideration of the general form of renormalized gravity with all corrections, which was what I call GR-EFT. Basically, it would be the theory which has all the infinite chain of counter terms of GR. Let me introduce some definitions regarding scattering of gravitons, because I will also refer to scattering amplitudes of 4 gravitons. I will give just results without the computations because, as I mentioned, three-point graviton vertex contain about, I think I did some recent computations on exact Mathematica package, and it was about more than 100 terms if you just expand it in terms of momenta. And 4 graviton has about 1,000 terms, if I remember. So it's not realistic to do it by hand unless you use some nice properties, which some people use. But in principle, given that there are packages which deal with tensor indices very quickly, maybe the most useful part here is if I give some links to Mathematica notebooks with codes for computing scattering amplitudes. But let me come first to certain definitions. What we mean by scattering of gravitons. As Luca mentioned, gravitons have 2 polarization vectors, 2 polarization states, which can be which can be classified by their helicity. And in the scattering process, we can also break down Lorentz invariance and see it into center of mass frame. Then for momenta of the four particles in the center of mass frame, if we choose this axis for direction of momenta of P1 and P2, then we have this form. And then if the scattering angle of the particles is theta, this momenta, they can be obtained just by rotation of these two by the angle theta. So that's for the momenta. We can also introduce polarization vectors. And if we use the vectors of plus minus helicity of momentum P1, its explicit form is 1/√2, 0, 1, plus minus I, 0. This vector is a vector which is transverse compared to this, compared to momentum P1, and depending on plus or minus, it rotates in a proper way correspondingly with its helicity. That's how I find this vector. And of course, the other vectors, like as the one of P2, can be obtained simply by rotation or by finding perpendicular vector to certain momentum. And then for the others, we need just to rotate them by the scattering angle. It's not yet graviton polarization tensors. It's just vectors from out of which it is convenient to construct the polarization tensors. They are also normalized by unity. So that's the explicit form of 4 polarization vectors, and the tensor graviton polarization tensor, which has 2 indices, is just direct tensor product of these 2 vectors. And there is no sum with respect to plus minus. It's just if we want positive helicity tensor, we just take E plus multiplied by E plus. So then if our theory is parity symmetric, we can have only 3 independent, linearly independent graviton scattering amplitudes corresponding to the scattering of plus plus to plus plus, plus plus to plus minus, plus plus to minus minus. I will call this one as plus plus minus minus, like because I want to use ingoing notations, like, which means that I also have to change the sign of polarization of the of the final state gravitons. Here I have one minus polarization, and the third scattering amplitude is has 4 pluses. Remarkably, for GR, the result is very short, though it's very difficult to obtain it by direct computation, because in order to obtain it, in principle, it can be done by writing some relatively simple mathematical code. The scattering contains 4 diagrams. S, T, and U channels of exchange diagrams. And in addition, there is a 4 vertex, which is still quite a very long expression if you try to obtain it by taking force variation of Einstein-Hilbert action. So all 4 amplitudes are important here. And eventually the result for graviton scattering is very simple, because this is 0, this is 0, and this is 1/np squared s cubed over tu. That's it. That's something which if everything is computed correctly in these 4 diagrams, where it is very important that the coefficients here and in 3-point vertices are tuned properly, as it is dictated by the symmetry of by the general covariance. We get this kind of structure for the amplitude. So it has a pole structure when t is 0 and when u is 0 in this, for this particular amplitude. But these amplitudes are not always 0, and the counter terms appearing in general relativity will bring here several non-trivial contributions, which we will see later. And now let me switch to the definitions of what is effective field theory and what are the rules of this game named effective field theory. Let's use first the toy model before coming to gravity to make it more explicit and understandable. Let's consider the non-renormalizable scalar field model with the most explicit structure, which is shift symmetric scalar field with a shift symmetry. The first interaction here, which we can invent, is box phi d mu phi squared, like cubic term. We also require that the theory is symmetric under the constant shift of the field. For this reason, we must have only derivative interactions in the theory. And in principle, we can write a lot of terms. Again, trying to renormalize this theory, we get into the problem that at each stage, to compensate divergences, we need to introduce more and more terms. That's why we have to introduce all of them starting from the beginning. Like here we have 4 derivatives. In principle, there could be some 6 derivative terms with some certain structures. And we will discuss what kind of structures we expect. But apparently, many structures can be eliminated from this consideration simply because some of the terms can be reduced to others by the use of total derivatives. For example, at the cubic level, in principle, we can have a term d mu phi, d rho phi, d mu, d rho phi. But I can reduce it to this one. How can I do it? I just take this derivative and omit the total derivative. So it will be d mu phi, d rho phi, d rho phi. And under the integral sign, I can simply eliminate this interaction. And then I have to, then d mu phi falls to all of this bracket. It goes to here. Minus d rho phi. And I have to differentiate this one, this term, and this term. And here I get minus d rho phi d mu d rho phi minus. And when I differentiate this one, I get d mu phi box phi and d rho phi. Sorry, So I reduced it to the term which I already have in the action. And this term apparently is the same as this. So this term here is exactly this one because I can simply exchange the definition of the indices. So I can simply relabel the indices. which means that since they're the same, then 1/2 of and 2 of d mu phi 0 phi d mu 0 phi is equal to minus box phi 0 phi squared. Of course, up to total derivative. So I can make it only under the sign of integral, but that's enough for me. I can simply substitute this term by that term and simply not write this in the effective action because it's redundant. So that's one possibility how to reduce the structure of effective action. Another possibility is that apparently I can also eliminate this term at all. I can my effective field theory expansion can simply start from d phi to 4 term. Let me show the trick. Okay. I will need this expression later, so I will leave it on the blackboard yet so far. So the trick is that in principle, in perturbation theory, I can make field redefinitions. And if in this theory I do a simple field redefinition, like phi is equal to new field high plus some coefficient a d rho high squared, it will not change my theory at the quadratic level. It will change just some, it will just reshuffle a bit the interactions in this theory. Quadratic propagator part will remain the same because this is considered as a perturbation or interaction. It's totally valid to make this kind of field redefinitions. But what is not allowed, for example, is to change phi to, I don't know, d mu high squared. If I do like this, it's not something that will bring me some meaningful field theory. So because this is not a perturbative field redefinition, it will change my propagator drastically. So it's not allowed to do this kind of transformations. But this one apparently is very helpful. So if I do this transformation, I get the Lagrangian. And let me now simply omit the total derivative terms. So at the kinetic term, I will get the same one, d mu high squared, same as d mu phi squared, minus, since this will be the next term, I need to substitute this change of variables to derivatives. So I need an expression for d mu phi, which will be equal to d mu high plus 2a d rho high d mu d rho high. And taking the square of this, I get the first term here. And also I'll get the mixed term as d mu high multiplied by 2a d rho high d mu d rho high. Okay. The fourth order term, let me just, for the moment, look only at high cube terms. Plus something of height of 4. Then in addition, I have my cubic term, my original cubic term with alpha. And it will, at the leading order, it will transform as d mu high squared box high. plus some terms which are higher order, up to higher order terms. And in principle, since I'm selecting myself what kind of transformation to do, it's up to my taste. I can adjust the coefficient A such that this term will be cancelled. Since I know this, I learned this kind of equivalence, I can simply say that my A is minus alpha, and thing is done. These two terms will just cancel each other. Okay, that's the trick which allows me to eliminate cubic interaction and transform it into higher order interactions. But there is an important thing to remember, that it's not just we throw away this term. We need to remember that if it was in the theory, it will contribute, it will be transferred to, its contribution will be transferred to 5 to 4 terms, 5 to 5, 5 to 6 terms, and so on. So higher order vertices can receive the contribution coming from these vertices. It's a kind of reshuffling of EFT terms, but it doesn't mean that it vanishes completely. And in principle, this kind of term will not contribute to tree-level scattering of phi fields, but it will contribute to higher point scattering. Still there will be some trace of this term in the EFT, but if we are interested mostly in 4-point scattering amplitudes, we can simply keep only terms which are contributing to 2-to-2 scattering. But still, we have to remember that there is a bunch of terms which do not contribute to scattering. But in principle, they can give contributions to loop diagrams in 2-to-2, because in principle, we can have we can imagine some terms like 5-point vertex contributing to 2-to scattering. So at tree level, we can forget about them, but if we want to consider properly some multi-loop diagrams in EFT, if someone gets crazy to study this, then we have to remember that there is a bunch of terms which also has to be included into EFT, because they will start to giving some contributions. So in this way, we can write much more compact non-redundant Lagrangian for EFT. It will start the first non-trivial interaction contributing to 2-to-2 scattering starts at the level of d mu phi to 4. The next term will be d mu phi squared d rho d sigma phi squared. Plus we add more derivatives and get more combinations, but apparently all of them are reduced to just one term up to quite high order. Then the number will be increasing, but not very fast. So how can I check myself that I haven't left any of redundant terms, or I haven't missed anything in the which appears in the EFT Lagrangian? In principle, the best test for this is to compute tree-level scattering amplitude. That's why it is also convenient to build one-to-one correspondence between the EFT Lagrangian and the amplitude. Apparently, all terms which are redundant through field redefinitions or so on, they don't give non-trivial contribution to the amplitude. And for this Lagrangian, I wrote this explicitly now, and I'm sure that I don't have more terms which can contribute to the amplitudes. How can I know this? The secret knowledge is that scattering of two scalars the scattering amplitude has STU crossing symmetry. So it means that if I exchange S and T and then T and U, I get the same amplitude. And there are just very limited number of terms which can satisfy this crossing symmetry in the scalar field amplitude. Apparently, all possibilities for polynomial amplitudes having STU crossing symmetry can be listed in the following way. The first non-trivial possibility is S squared plus T squared plus U squared. And this is some contribution corresponding to which should be suppressed by force power of the cutoff scale, just by dimensions. The amplitude is dimensionless quantity, and simply by dimensional analysis, I can say that the only term which is suppressed by lambda to 4 and contains 4 derivatives can be written in this form. There are no other possibilities to write it, and I cannot write a polynomial in STU of the second degree such that it's not reducible to this one. Of course, here I need my theory is massless, and I also need this condition. This condition basically forbids operators suppressed by lambda squared because this is simply the only trivial combination, and it's just 0. So I know that this term is unique, only one term. Only one term, and I already have written it. Then I build it. I go to the next order, and the only invariant I can construct is STU. S cube plus T cube plus U cube. You can check yourself when you have free time. It's simply reducible to that one under the condition that S plus T plus U is equal to 0. So this is reducible. And this one is 1 over lambda to 6 and corresponds to 6 derivative terms. Again, knowing this, I obtain that 6 derivative contribution is the only one. It's only one term, so it's again only one possibility. And all further amplitudes, I can construct them out of these variables. Let me call this x and this y. Crossing symmetric variables, and it will be simply a polynomial of x and y, and then I can just count dimensions of these terms and find out how many possibilities I can have for EFT coefficients. Then I write technically I can write two proposals for this kind of the corresponding number of EFT terms and check that they are not reducible to each other by direct computation of the amplitude. So at D26 I have only STU. At the next order I have STU multiplied by x. It will be 1 over lambda to 8. Again, only one combination. Because I cannot write anything else. So I'm sure it's only one term. I already have it. Then I can have x squared term, and again, it's only one possibility at the level of lambda to 10, and again, I'm sure that it's only one term. Things will be a bit more complicated at 1 over lambda to 12. It's the first possibility to have two different terms, two different structures, like STU squared or S squared plus T squared plus U squared cube. They have the same mass dimension. That's why for the next term I need to write two terms. But it's quite a long work to find them and identify that they indeed contribute non-trivially to two independent combinations. That's practically what you need to do if you need to build some construction of EFT. If you know the symmetries and know what are the terms, what is the structure of that. I just wanted to show that knowing some properties of scattering amplitudes helps a lot, because I don't need to check that, reduce manually many terms to just one, because in principle I can write a lot of combinations of covariant derivatives. So this secret knowledge about amplitude simplifies my life drastically. And another very important knowledge about the amplitudes would be that if I have some terms proportional to free equations of motion, like here, this term is apparently proportional to free equation of motion, box phi equal to 0. Then the rule is that I can eliminate these terms by analog of this kind of field redefinition. So one of the rules of the EFT game is that in EFT, you have an opportunity to eliminate all the terms proportional to free equations of motion. That's another secret knowledge of EFT people, that once you see something proportional to equations of motion at tree level, you can simply eliminate these terms from the EFT and simply not write them in the expansion, because they will not contribute to the amplitude on shell. And in this case, the field redefinition can be adjusted also very easily. In the very general form, let me write it. If we have a term proportional to free equations of motion, let it be some functional of phi, maybe with indices. This is operator corresponding to equations of motion. So we have equation of motion of this type. And the fact that it's a free equation of motion means that my Lagrangian has a form phi 1/2 phi e phi in this very general formulation. Then I can make a field redefinition of the following form: phi equal to chi plus 1/2 f of chi. And simply doing the same trick as we did with the shift symmetric scalar, eliminating cubic term, we can explicitly get that this term will be eliminated, because the same term will appear from kinetic operator of field phi. So we can achieve this cancellation. So this knowledge is very important for the construction of gravitational EFT, because gravitational EFT is much more complicated thing compared to theory of one scalar, where in principle you can, for the finite time, you can simply take all terms with all derivative combinations and handle this brute force computation. But in gravity, it's much more complicated. So how can we do it in gravity? First of all, the most general effective action, let's just write what we can write. We had, of course, our Einstein-Hilbert term, then a bunch of quadratic terms. In principle, at the same mass dimension, we can write also some strange term box R, but also we can immediately see that it is a total derivative. So it can be eliminated very easily. And then we have some structures like Riemann cube. But let's first check what's happening with quadratic terms. Even if it's a gravity theory with matter, recall that equations of motion are Einstein-Hilbert equations. And given this, T mu is some of something corresponding to matter fields. Also, we can find that for curvature, it's 1/2 1/p squared t, where it's a trace of energy momentum tensor. But the main point is that. Yes. Okay. The main point here is that these are free equations of motion. Free in the sense that we can expand everything in gravitons, but it's easier to keep it in a covariant form. But then, as we learned in general, that all terms in the EFT which are proportional to free equations of motion can be simply eliminated. Basically, this means that R squared can be substituted by some matter combination. R mu squared also corresponds to some matter combination. And in the if there is no matter in the theory, it's simply zero. So we can see in this way we can eliminate or move to matter sector the terms which are proportional to R squared and R mu squared. So these terms are irrelevant for the EFT considerations and amplitudes. In 4 dimensions, we also know that there is a Gauss-Bonnet combination, which is a total derivative. And apparently, the presence of this Gauss-Bonnet combination, G term, it is R squared minus 4 R mu squared plus R mu lambda rho squared. The presence of this total derivative of something means basically that we also can eliminate R mu lambda rho squared term in 4 dimensions. So in EFT of gravity, there are no quadratic terms. And here we have, okay, just a couple of minutes left. I can simply explain the situation because I guess this is quite a strong conclusion that there are no relevant terms for EFT consideration of gravity at quadratic level. You can move it to some matter interactions. Yeah, t squared. What depends on what matter you have. It's not a gravity part of the Lagrangian anymore. Yes.
Usually in the literature, the box are, if it's a total derivative, why is usually the literature?
It can be eliminated only under the sign of integral. So if people are computing, say, trace of energy momentum tensor or anomaly, you cannot simply eliminate it this way. You can throw it away only if you have integral and action. Or even in equations of motion, you have to keep these terms. But building the action is a bit easier because indeed you can throw away many things. So I guess later during this school, there will be some statements about quadratic gravity, including renormalizable quadratic gravity, which is defined basically as Einstein-Hilbert term plus all this bunch of these square terms. This allows to have gravity with propagator more suppressed than NGR and make it renormalizable by the price of some extra degrees of freedom ghosts. I think there will be some mentions in detail about this story, but what's the difference? Why why I can say that in EFT I can throw these terms away, but in some other framework it can be even renormalizable UV complete theory, though non-unitary, but still a very nice example. What's the difference? The difference is that EFT concept deals with first with defining what are the fields in the low energy action. What are the degrees of freedom? And the EFT I'm considering now is an EFT of two polarizations of graviton. No more polarizations, no massive gravitons, no ghosts, nothing else. Only these ones. If you seriously consider these higher derivative terms from the point of view of like starting from equations of motion, you write equations of motion for quadratic gravity and you get more degrees of freedom in principle. Of course, well, this is not a good theory. Some of them are ghosts, but still, from the formal point of view, you have more degrees of freedom, and the proper EFT construction for that would be either integrate out of these degrees of freedom if they are heavy, or deal with somewhat different EFT having also these massive graviton ghosts or whatever. But it will be a completely different EFT with their own interactions and additional interactions of them. And of course, once we define that we are dealing with low energy theory of graviton scattering, and we determine that we have only two polarizations of gravitons, we can do all these tricks. This is the rules of the game. If we want to consider some other theory first at the level of propagator, then it corresponds to a completely different EFT setting. Okay, I think we can have a coffee break now, right?
The question online
Okay.
before you continue. So it's asking essentially why you include Riemann cube but not other terms. But
I will explain it in the beginning of the next lecture, but in general it was just schematic schematic definition, meaning that I gonna consider all cubic terms. But the short reply could be that only Riemann cube terms will survive because Ricci and Ricci scalars will simply be reduced to matter interactions, as I just have done with quadratic terms.
But in this case, you describe only gravity, no
scalar field. Scalar field can be encoded in this T menu, but it will be some.
Not eliminate this term.
I cannot eliminate this completely, but I can eliminate this from graviton interactions. It will be a matter interactions, or matter not pure gravity interactions, but either matter interactions or matter gravity interactions.
You mean they will not contribute to the only graviton scattering?
Yes. If I consider at this moment only gravitons, I can do this.
If you get to this term in string theory.
Yes. Of course.
They also don't contribute to even.
Well, maybe only at loop level, but at tree level, no.
They would be proportional to S plus T plus U.
Yes. Well, that's the meaning of being proportional to equations of motion, basically.
I mean, once you have this Lagrange, what do you want to do with this Lagrange?
I want to consider scattering amplitudes and structure of these amplitudes and discuss some constraints on Wilson coefficients of this theory. So first I need to write some minimal setup, and then the problem which I will be solving would be how to what kind of EFT can we have? What kind of EFT is compatible with some meaningful UV completion? And that's I will discuss tomorrow in more details. I'll introduce positivity bound framework where I can get some. I can say something about which kind of Wilson coefficients are allowed in normal quantum field theory and which are not allowed.
You need the Lagrange.
I need to define what are my operators and what is the structure of the amplitude for this.
You start from S.
I can do both things in principle, but
You use the same reasoning for the Lagrange.
as in most cases I can, but first I need to know the structure of the amplitudes. It's a bit different because this one is TU symmetric. These two are fully crossing symmetric. It's but the GR result it's not yet clear, but for EFT result it will be more clear. In principle I can, but in practice there are some surprises, like some structures and amplitudes cannot be reproduced by local Lagrangian. I'll give an example after coffee break, I think.
This term there, you can compute in for the gluon. And for the gluon is much simpler. And then you do KLT and you get the gravity.
Mm,
Let's maybe discuss that over coffee.
yeah, maybe.